Okay, take a moment to jot down this information. We are looking at analyzing a discontinuous derivative. So we're given a derivative graph, which you see down below here, and you can see it's discontinuous at x equals 0 and at x equals 2. So down here you see the domain, all right? This is the union symbol, right? So we're just linking all of these intervals together. So at x equals 0 and at x equals 2, it's discontinuous, okay? We have some jumps going on there. So we can see here that our derivative graph is between -4 and +4 for x values. So suppose we're told that f is continuous between -4 and 4. All right, so there's no discontinuities on f. Now, f prime has some discontinuities, but not f. We are looking to find the x coordinates of all local extrema and points of inflection on f, and then we're looking to sketch a possible graph for f. So again, hit pause, copy this down for a moment. Okay, so let's first start by finding local extrema. Oh, and by the way, on our graph here, this crosses at -3, and this is crossing at -1. Okay, so those are the roots. Okay, so to help us analyze this, let's start by making a sign diagram for f prime. And we're going to contain this between -4 and +4. Okay, so we can see here that at -3, our derivative value is 0, and at -1, our derivative value is 0. Again, that's where f prime is hitting the axis there. Okay. Now, other critical points here. After -1 here, we know that 0 is a critical point because it's undefined. So we'll put that undefined symbol above 0, all right, that null set or that empty set symbol, all right. Now, if you write DNE above it, that's the same idea, okay. 1 is a critical point because at 1 the derivative is 0, and then 2 is a critical point because at 2 the derivative does not exist. Okay, so let's go through and let's get our signs. Okay, between -4 and 3, we can see our derivative is positive since it's above the x-axis. Between -3 and 1, we see how it's below, so we have a negative derivative there. Between -1 and 0, it's above, so it's positive. Between 0 and 1, it's below, so that would be a negative. Between 1 and 2, it's above, so that's a positive. And then between 2 and 4, we see it's below, so that's a negative. Okay, so let's identify our local min and max points. Let's start with our local max. We know we're going to have a local max when the first derivative goes from positive to negative. So that happens at x equals -3, 0, and 2. Again, this means we're increasing, then we're decreasing. Increasing, decreasing, increasing, decreasing on f. So you can see that your max points would be at -3, 0, and 2. All right, our local min, well, that's where the derivative goes from negative to positive. So we would have -1, and we'd also have +1, but we're also going to have these endpoint values. So -4, -1, +1, and 4 would all be local min. So the endpoint values, remember, we're starting off with at -4, we know that it's going to increase. So there's a local min there. And we're ending at 4. And since the function here is decreasing, since we're decreasing, okay, there's going to be a local min here at 4 somewhere. Okay, so we have all those values for local min. Okay, the endpoints are included. Again, think about how the function is either increasing or decreasing. Now, for our inflection points, let's keep in mind that we need the second derivative and we need to know where the sign is changing. Okay, so now you need to be thinking in terms of the derivative. Well, at x equals -2, All right, this equals an inflection point because the second derivative changes sign. All right, look at the slopes of your tangent lines. You're going from an area here where it's negative to positive on each side of -2. So there are no additional points where the second derivative changes signs. As you go along this function here, you can see here there's a positive slope everywhere. Down here there's a zero slope. Okay, so at x equals -2, that's the only time the concavity is changing. Okay, so if you were to do a little mini sign diagram for your second derivative, we would plop -2 down there. The second derivative is 0. Okay, to the left of it, we have negative slopes. All right, and then to the right of it, we have positive slopes until we actually hit a value of 2. All right, after 2, between 2 and 4, let me just cap this here at 4 and go back over here to -4. Between 2 and 4, there isn't any concavity. All right, you would actually have all zeros there. Okay, because again, back up here, this slope is 0, so that's neither positive nor negative. Okay. Now, let me add here that above 2, we're going to show that that is undefined there, since the derivative at 2, all right, the derivative of the derivative, well, it's not continuous, so therefore there can't be a derivative there. Okay. All right, so now we want to try to sketch a possible graph for f, and we're told that it's continuous between -4 and +4. So we're going to use both of these sign diagrams. We're going to try to put these pieces together. The key is to try to plot as many points as you can, all right, to just take it one step at a time. So let's first look between -4 and -3. Well, between -4 and -3 up here in our first derivative, we know it has to be increasing, and down here we know it has to be concave down. So, and we also know that at -3 we need to have a local max. So it has to be increasing and bent downward. All right, so it might look something like that. All right, so now between -3 and -1, it has to be decreasing. Okay, and we know that over here the concavity has to change at -2. So it needs to first be concave down and decreasing. Okay, so it's going to be concave down and decreasing, and at -2 that concavity is going to change. At -1 we know that we're going to have a min from up above, so here's -1, let's say. Okay, so our concavity is going to need to change, okay, right here at -2. Okay, so again at -1 we have a local min. All right, so as we work our way across here between -1 and 0, we know that, well, at 0 it's not going to be defined, okay, or the derivative rather is not going to be defined. So you got to be thinking, all right, sharp turn. Okay, so it has to increase, and over here we know it has to be concave up. So at some point here, concave up and increasing, we need a sharp turn. Over here at +1, we know that we need to have another local min, and we know that between 0 and 1 it needs to be decreasing. And if you look between 0 and 1 here, we're still concave up. So decreasing and concave up would look something like that. Okay, so there's our local min at 1. And again, we have a sharp turn right there at x equals 0. Okay, so from there, we know as we look between 1 and 2, we have to be increasing. And again, still concave up. And at 2, we're going to reach another local max, but at 2 we said that the derivative doesn't exist, so we need another sharp turn, okay, something like that at +2. And then from 2 to 4 we know that it needs to decrease, and notice that the concavity here is 0, so that means it doesn't have any concavity. So that means it's not bent upward, it's not bent downward. So what that must mean is that you have just a straight line, okay? So there's no concavity, it's not bent up, it's not bent down, it's just a straight line here. So you have a sharp turn, and then it just shoots straight down, okay? So we have two sharp turns. That's where the derivative doesn't exist, okay? So this would be a possible graph for f.